So what we would like to look at here is Chapter 1, Relations and Functions, Section 1.3, Functions. We talked a lot last time about relations. A relation is simply a set of points in the plane. A function is a special kind of relation where when I take any 2 points that have different y coordinates, they will also have different x coordinates. So in other words, what I've got here is a function is a relation where each x coordinate is matched with only one y coordinate. In this case, we would say that what we have is y as a function of x. Let's take a look at an example here. I've got 4 different points here. All 4 of these points have different x coordinates, and not one of them is going to be 2 different x coordinates with the same, not one pair is going to be 2 different y coordinates on the same x coordinate. There's no other point that has the same x coordinate as this one, or this one, or this one, or this one. You'll notice that these 2 have the same y coordinate, and that's okay. They're 2 different x coordinates, so we're totally good. What I can't have is this. This point right here is a problem because when I look at these 2 together, they have the same x coordinate, but 2 different y coordinates. That's not a function. The idea of a function is that I'm supposed to be able to, for every x coordinate, come up with the y coordinate, like we're thinking about an input and an output. But if I were to input this x coordinate here, I wouldn't know if I'm supposed to come out to this point or to this point. So that can't possibly be a function. Graphically, we see the issue here. It's that the 2 points are above and below each other. In other words, I draw a vertical line and it passes through both of them. In a function, this will never happen. Therefore, what we've got is the vertical line test. If a function has a vertical line that hits 2 points, then it actually isn't a function at all. Otherwise, we'll say that it is a function. We can have relations that aren't functions. We can have relations that are functions, but it's functions that we're going to study most closely in this class. The other property of functions that we're going to pay close attention to is domain and range, which we can think of as input and output. If I have a function, the set of x coordinates, or the inputs, would be called the domain, and the set of y coordinates, or the outputs, would be called the range. Again, x and y don't have to be used here, but when we're thinking of the typical graph of using x and y, then that's what we're going to be thinking about. Let's take a look at a couple of examples. We'll start simple here. I've got 2 different relations, f and g, and I would like to be able to find the domain and range of each if they are a function. Let's take a look at f, and we're going to look at each of these 2 graphically first. F is going to be, looks like it goes up to 5 in each direction, so we'll start by labeling our axes and throwing a scale on. Okay, so I've got the point 1, 1, 2 minus 4, 5, 1, and minus 2, 4. All 4 of these points are not the same x coordinate. No vertical line would ever pass through more than 1 point. We're good here, we're good here, we're good here, we're good here. So yes, f is a function. The domain is the set of x coordinates. So I see -2, I see 1, 2, and 5. The range, the set of y coordinates, I see -4, I see 1, and I see 4. It is perfectly okay that these 2 points share a y coordinate. I do not care if that happens. That's perfectly okay. Again, thinking about inputs and outputs, I would say that 1 has an output of 1 and 5 has an output of 1. That's totally okay. Let's take a look at G now. If I'm looking at G, again, I'll make sure I'm labeling here. And I should really even just say this one is F and this one is G, so it's super clear. Looks like I go up to 5 either way. And then I'll need to go up to 6 here. Okay, so now I've got the point 1, 3. 3, 1, 0, 2, 4, and 5, 6. Immediately graphically, I can see we do not have us a function. These 2 points have the same x coordinate, but different y coordinates, and they are on this same vertical line. I can see on these points here, same x coordinate, but different y coordinates. That's not a function, so we'll move on. If it's not a function, it can't possibly have domain or range. This time the function was given to us not as an actual set, but as a graph. So we'll have to take a look at this function and figure out what the domain and range is graphically. First of all, I can see visually that there's no place where a vertical line would pass through the function more than once. So it is going to be a function. Now to find the domain and range, I'm looking at x coordinates and y coordinates. What I like to think about here is what would happen if I took a shadow of the function. Imagine for the x coordinates that we're looking at the shadow where the light source is from above. And then for the y coordinates where the light source is over here. What would the projection be of the shadow of this graph onto a wall? If I was going to do, let's do first the x coordinate. So if I was going to project downwards onto this wall down here, what I see is that this is the rightmost point. It's not included because I've got this open circle. And then this is included, this is included, this is included, and it looks like it keeps going. So what I've got right here is this. This looks like one of those intervals that we were graphing at the very beginning. And so what I've got is an interval that starts at -infinity, comes in and goes left as far as it would want to go, and then it's going to end at 1. And at 1, it's going to be open because 1 is not included as an x coordinate. We can do the same thing for our y coordinates. This looks like the lowest one, and it is included here. I would say that at 0, the y coordinate is 2, so that's included. This will come over next. Even though this point is not included, this one is. So we are going to include this. And then this looks like it's good, this looks like it's good, and it looks like it's just going to continue upwards forever, again, following that arrow. So I can connect the dots as I did before. And again, what I've got myself is this interval. It's vertical this time instead of horizontal, but that's okay. Looking at this, it looks like the lowest point is -2, and it goes on forever. Remember, we cannot include infinity because it's not a number, so this just symbolizes that we're going on forever. Now what I'd like to do is be able to do the same thing but with an equation. We could graph the equation and see what's going on, maybe using a graphing calculator, but we don't know how to graph this type of equation by hand. So since we don't understand how we would graph it, we want to be able to solve this as if we would be able to do it by hand. What you're going to do for this type of problem is you're going to think about if you can get that same idea where you've got an input and an output. That means that what we would like to be able to do is we would like to be able to solve for x, get x by itself. That means the first thing I'm going to do is I'm going to subtract x cubed from both sides. And then I'm going to need to take a square root. Now remember, whenever you take a square root, you need a plus or minus. So y is equal to plus or minus the square root of 9 minus x cubed. And now I've got myself a problem. What if x was 0? Then y would be plus or minus the square root of 9 or plus or minus 3. That's not going to be two unique x values. That's the same x value with two different y values. And graphically, I don't know what the entire graph looks like, but I do know that when x equals 0, I've got 3 and -3 on the same graph. That's not going to be a function. So we would write not a function. Let's try a similar example. This one looks a lot like the last one. They've just changed up a couple of things here. I need to be able to, again, solve for y. So let's go ahead and subtract the x squared on each side. Y cubed is equal to x plus 4 minus x squared. And now I'll take a cube root. Now recall that cube root doesn't need a plus or minus, because if I was to multiply 3 negatives together, I would get a negative, or 3 positives would get a positive. So plus or minus doesn't make sense for a cube root. We don't need it. That means y is simply equal to the cube root of all that junk inside. There's no plus or minus. There's no question. If I put in an x value, I know exactly what y is going to come out, and there's only one option. That means, yes, it is a function. Let's do one more. This one looks a little bit different than the last one. I'm not exactly sure what to do at first. We need to think of how to solve for y. Now, when you're not sure how to do this, you want to try to think back to your basics. You know when you're trying to solve for y, what you want to do is you want to put all of the thing you're looking for onto one side. So let's first move this over on both sides. There's no like terms to combine, so I simply have xy plus 3x squared y. Now, you might see what the next step is. I've got y multiplied by x here, and y multiplied by 3x squared here. That means that I can pull a y out, basically doing the distributive property backwards, factoring y out to obtain x plus 3x squared. And now it's clear how we should solve for y. By dividing this extra stuff over, I get y by itself. Great. I never did a square root. I never did anything where there would be a question about whether or not there were multiple answers. So I do indeed have a function. That's all we have for today. I'll see you guys next time.